Welcome to IPMWORKS e-learning modules. My name is Nicolas Munier-Jolin from INRAE in France. This video is part of module number 3 about integrated weed management. And this is chapter 5 about the case study for weed management, the long-term experiments for weed management in arable field crops in Dijon, France, from 2021 to 2018. This year is 18 years of experiments for integrated weed management-based cropping systems. Integrated weed management implies to redesign cropping system by combining many non-chemical weed management measures, the very famous many little hammers for weed management. For example, diversified crop rotation, soil tillage, using plowing and the false seed bed technique for reducing the seed bank, adapted sowing dates for escaping weed emergence, or mechanical weeding, and we will see that there are plenty of other non-chemical methods. When you are redesigning cropping systems to combine those many little hammers, this raises many questions. First of all, is the combination of many little hammers efficient to control weeds on the long term? Because we know that weed management is a long-term management over several years. Second question, how much is it possible to reduce herbicide inputs thanks to integrated weed management? Are integrated weed management-based systems cost-effective and profitable for farmers? Are they increasing workload for farmers? And finally, are there any drawbacks of those integrated weed management systems for the environment? Are there some unexpected environmental impacts? The long-term experiments in Dijon started in year 2000 with the first harvest in 21, was designed to address those questions. The design was with 5 cropping systems that are described on the left of the screen. System number 1 is considered as a reference standard with crop rotation typical for the region where we are in Dijon, Burgundy. This reference crop rotation is oilseed rape, and then wheat, and then winter barley. And cropping system 2, 3, 4, 5 are supposed to be integrated weed management based, but with different options and strategies. For system number 2, we implemented integrated weed management with reduced tillage, no plowing, and this system changed along the 18 years of the experiment. At the beginning, it was reduced tillage with only shallow tillage operation, and in the beginning, in the middle of the experiment, around year 28, this system changed to no-till system to investigate whether it's possible to reduce herbicide use in no-till systems. System number 3 is integrated weed management with no constraints on soil tillage. Plowing is used in this system, not every year, but in some years over the crop rotation. The constraint here in system 3 is that there is no mechanical weeding, because we were thinking that many farms have not the proper equipment for mechanical weeding. Mechanical weeding can be time-consuming, so we thought it was interesting to investigate whether integrated weed management without mechanical weeding could allow a proper weed management with reduced herbicide use. System number 4 could be called full integrated weed management. We tried here to use all the non-chemical approaches for weed management, including mechanical weeding, and herbicides can be used here as the last option for weed management. And finally, system number 5 is a system with no herbicide at all. Each of those 5 systems are implemented on 2 fields. We had 10 fields in this experiment. Each field is about 2 hectares. We have 2 repetitions of each system. The soil type is a clay limestone soil with a depth of 0.6 to 0.9 meters, with quite a high yielding potential. And the initial weed community is presented below, with quite a diversified weed community, with blackgrass as the main winter emerging grass. But we have also, for example, many weeds typical from cereal crops, such as Gallium aperone, Veronica species. We have Cirsium arvense as a perennial weed, and we have a number of summer weeds, such as Clinopodium album or Solanum nigrum or Amaranthus species or Polygonum species, because of the history of those fields with some summer crops and winter crops in the crop rotation. Here you can see an attempt to describe the technical differences across cropping systems. You have in this figure on the bottom right system number 1, the reference standard system, which is quite linked with the percentage of winter crops, because the crop rotation was winter oilseed rape, winter wheat, and winter barley. Also quite correlated with the amount of nitrogen applied, quite related with the plowing frequency, because plowing was used quite often in the crop rotation. And this is quite different as compared to the other system 2, 3, 4, 5, with 2 systems that are quite close together, system 4 and system 5, with quite a lot of soil tillage operation, harrow in the crops for mechanical weeding here, and hoeing, and a rotary hoe, which was all mechanical weeding operations that are quite frequent in those 2 cropping systems, number of fall seedbed techniques, and so on. And those soil tillage, of course, are negatively correlated with system 2, which is a system with reduced tillage at the beginning of the experiment, and then no till at all, and no till, and of course no mechanical weeding. Whereas system 3 and 4 are more related to the diversity of sowing periods, with more spring crops in the crop rotation, more summer crops in the crop rotation, delayed sowing of winter cereal to escape autumn emerging weeds. And that's it, more or less, to describe the diversity across those 5 cropping systems. Here you can see presentation under the presentation of system number 4, which is full integrated weed management. You can see that the crop rotation is diversified to a 6-year crop rotation, or even 12-year crop rotation. We have rape in the crop rotation every 6 years, and then winter wheats, and then a summer crop with maize or soybean, and then again winter wheats, a spring legume crop with faba bean here, and then a critical, quite robust cereal here. To come back to rape, you can see all the aspects. So we have a diversified crop rotation with 5 sowing periods from summer sowing, middle of autumn sowing, late autumn sowing, spring sowing, and end of spring sowing with maize or soybean. So which it makes 5 sowing periods. We have the alternation of plowing and shallow tillage along the crop rotation. You can see that before winter wheat and triticale, we implemented shallow tillage, whereas after the wheat and after the triticale, we tended to plow to use the plowing to bury the seeds that were produced by weeds in the winter wheat, so as the weeds are in the deep layers of soil before sowing the next winter wheat. Winter wheat was sown quite late after fall seedbed to escape autumn emerging weeds. We had cultivar resistant to disease and competitive to weeds, and this made it possible to sow with a high density of plants for cereals, and cereals were mechanically weeded with spring-chin harrow or rotary hoe. We had mechanical weeding also in maize, for example, on soybean. For spring faba bean, we had bound spraying application of herbicide at sowing. So no herbicide in between rows, and in between rows, mechanical weeding using the hoe to control weeds in between rows. Triticale is known as a quite competitive cereal against weeds, and there also we had a mechanical weeding and most often no herbicide in triticale. This is a presentation of the typical the principles of weed management in system number four. So now I will present some results about those 5 cropping systems on different evaluation indicators. And the first one is herbicide use over 18 years. Here you have a figure with the treatment frequency index for the 5 systems over the 18 years of the experiment from 2001 to 2018. You can see that TFI in the reference system for herbicide is about 2, which means an average of about 2 treatments at full dose in this reference standard systems. Here you can see the distribution of herbicides among glyphosate, herbicide against dicot plants, herbicide against grasses, and large spectrum herbicides in red. You can see that herbicide use was almost not decreased in system number 2, with reduced tillage and no till in the second part of the experiment. But herbicide use was quite heavily decreased in system number 3 and system number 4, and of course in system number 5. It was divided by 2 in system number 3, which corresponds to the target of the farm to fork strategy for halving pesticide use, and it was divided by 3 for system number 4. So we concluded that integrated weed management indeed made it possible to halve herbicide use. We have shown that mechanical weeding in system number 4 as compared to system number 3 allowed to decrease TFI by about 0.3, but herbicide was not reduced in no-till system. Here you have the evolution of weed communities along the 18 years of the experiment. You have on the left the weed density in plants per meter square for all the 5 systems. You can see here that weed were controlled at a low level in system number 1 in most years, even though in some occasions we could have 1 year of bad control with quite high weed density in system number 1. Weed density tended to be higher in integrated weed management based systems from systems 2 to 5, but with no clear tendency of lose of control of the weed community. For example, if you look at system number 4, where herbicide use was strongly decreased, you can see that there is no big trend of lose of control of the weed demography over time. And it is the case also in system number 5, even though, for example, in system number 3, you can see in 2 or 3 occasions some loss of weed control during 1 year for one crop. You can see on the right species richness, which tended again also to be higher in system number 2 to 5, and we will come back to this indicator later. Here you have a representation of changes in weed communities along time. Here you have a figure representing weed communities after weed control in crops during years 2012 to 2017. You can see that system number 1 is mostly related to weed species with autumn germination and quite low height, such as Veronica hederifolia and other Veronica species, Viola arvensis, or blackgrass Alopeculus myoturoides. You can see that in system number 2, with no till, and this period, the weed community is quite heavily different from system number 1, with more perennial weed species, and also grasses, for example, Lolium perenne or Echinoclora cruzgradi, and also many Asteraceae, such as, for example, Fungus species. Weed communities in system number 3 and 4 are not so different from weed community in system number 1, even though, for example, Polygona aviculare is more, which is a spring emerging species, is much more present in system number 4 as compared to system number 1. And weed community in system number 5 with no herbicide at all is quite different from weed community in system number 1, with more perennials and particularly Rumex species, and also spring and summer emerging species such as Solanum nigrum, and also maybe species with high sensitivity to herbicides such as Pilaria media. So you can see here that over a long duration of experiment, we were able to show quite heavy changes in weed community. Here you have a representation of species richness in the different systems. You can see that species richness, number of species observed in the field is significantly higher in cropping system 2, 3, 4, 5 as compared to system number 1. If you look at difference in number of species observed at different scales, at the scale of quadrats in a given year, you can see that going from system 1 to integrated wind management based systems, you increase the number of species per quadrat by about 2 to 3 species. If you look at the number of species per field and per year, going to integrated wind management increases the number of species by 5 species to 7 species, whereas on the pluriannual scale over several years, the number of species that were observed per field increased in system 2 to 5 by 10 to 14 species. This slide is about the estimation of yield losses due to weed competition. It is always very difficult to estimate yield losses due to weed competition. Here we try to estimate yield losses with the information of weed biomass. You can see here on the left of the slide the presentation of the weed biomass. You can see that in system 2 to 5, weed biomass tended to be significantly higher than weed biomass in cropping system number 1. And we used relationships that are presented on the in the middle of the slide. We established a relationship between weed biomass and crop biomass. The more weed biomass we have, the less crop biomass. And we used this data to estimate the crop biomass loss that can be attributed to the competition with weeds. And we use this loss of crop biomass as a proxy of yield losses. And based on this, and with the weed biomass measured on different quadrats, we were able to estimate an average crop biomass loss due to weed. And we can see that this crop biomass loss due to weed was about 0% in cropping system number 1, and ranged from 1% in cropping system number 3 to 7% in cropping system number 5. It was limited to 1% in cropping system number 4. So in cropping system number 4, for example, we were able to divide by 3 the use of herbicide by having a very limited yield loss due to competition of weed. So we could conclude, based on those results, that weeds were quite satisfactorily controlled in those low herbicide use systems. So now we can go to another indicator of evaluation of integrated weed management-based systems. Here we studied the emission of greenhouse gases using a life cycle assessment method. This assessment is important because if we are using mechanical weeding in integrated weed management-based systems, we could be aware of using more energy for mechanical weeding, and so this has to be assessed. We made some life cycle assessments based on the first 6 years of the experiment on all systems, and we expressed with the life cycle assessment the emission of greenhouse gases expressed as kilograms of equivalent CO2, and we compared over those 6 years the 5 cropping systems with the 2 repetitions. And the main finding of this are, first of all, that the emission of greenhouse gases per hectare of crop tending to be not higher, but with a trend to be smaller in system number 2 to 5 as compared to system number 1. And this was due to the fact that, by the way, the emission of CO2 linked to the machinery and the equipment and the fuel in orange in this figure, you can see that it is quite a small proportion of the emission of greenhouse gases. The most part of the emission of the greenhouse gases are linked with nitrogen fertilizers, both because of the energy cost of the fabrication of nitrogen fertilizers, and also quite a big impact of field emissions of N2O after nitrogen fertilizers that also has quite a heavy weight in the emission of greenhouse gases in the field. And in integrated wind management-based systems, we tended to use less nitrogen fertilizers, both because we diversified the crop rotation by including a legume crop in the crop rotation. You have seen in the previous slide that we introduced, for example, faba bean or soybean, which are legume crops which do not need any nitrogen fertilizer. And also, we tended to apply less fertilizers in cereal and mainly in winter wheat, because when we delayed sowing of winter wheat, we also were aware of delaying the yielding potential of the crop, of the wheat. And so we also reduced nitrogen fertilizers accordingly. So the conclusion here is that integrated wind management does not increase greenhouse gas emissions, and that nitrogen fertilization is the main factor of greenhouse gas emissions in arable field crops. So if you are aware of greenhouse gas emissions, don't worry to use one pass more of mechanical weeding, but alternatively, it's more important to look at how to reduce the nitrogen fertilizers at the cropping system level. Next slide is about workload. Here we present some figures of workload in terms of hours per hectare. So you can see that in system 1, the workload was estimated at about 6 hours per hectare and per year. This workload was tended to be reduced in cropping system number 2 due to faster sowing and to the absence of soil tillage, of course. It was also reduced in cropping system number 3 due to reduced plowing frequency, due to the reduction of the number of pesticide treatments. And of course, we had more frequent shallow tillages as we have seen, but still this did not compensate it for other factors. In cropping system number 4, the workload was almost similar to cropping system number 1. And we had an increase in the workload in cropping system number 5 because of the harvest of alfalfa. I forgot to say that in cropping system number 5, with no herbicide at all, the crop rotation was modified during the experiment by introducing alfalfa during several years, 3 years, by the way. And this was because we had some problems of development of thistle, this perennial weeds, thistle, and we introduced alfalfa to as a measure to control thistle. By the way, it was very efficient, but it had some impacts here on the workload because of the harvest of alfalfa, with 3 to 4 harvests of the alfalfa. So the conclusion would be that we did not find any real increase of workload in integrated weed management-based systems. And another aspect that we have to underline is that in those diversified cropping systems, workload is more evenly distributed over the year because of the diversification of crop rotation and the diversification of growing periods of the crop in the crop rotation. Now let's go to the end of the evaluation of those cropping systems with the economy and the indicators of cost efficiency. So let's have a look to the pesticide cost. Here you can see pesticide cost in euros per hectare and per year. You can see that in cropping system number 1, we had a pesticide cost of about 170 euros per hectare and per year. And those pesticide costs were quite heavily decreased in cropping systems 2, 3, 4, 5 on this period. You can see that interestingly, integrated weed management allows, of course, to decrease herbicide costs. The green parts are the green bars here that were decreased, and the less herbicide you use, of course, the less herbicide cost you have. But also the other components of the other pesticides costs were reduced. Fungicides were reduced because, for example, when we delayed the wings of weeds to escape weeds, we also delayed. We also reduced the risk for fungus disease in wheat, and also reducing fertilizers in wheat also tended to reduce the pressure of fungal disease. We reduced insecticides in all cropping systems, mainly because of the diversification of the crop rotation with less rapeseed in the crop rotation. We reduced quite a lot growth regulators that were almost not used in those integrated weed management-based systems, and we reduced anti-slugs, except in cropping system number 2, or during the last part of the experiment from 2007 to 2018, where we were in a no-till system, where we had many big problems with slug and needed anti-slugs to control those pests. Here you have a vision of input costs, combining pesticide costs, fertilizers, seeds, equipment, fuel, and irrigation. And you can see that the input costs were about 700 euros per hectare and per year for cropping system number 1, and was not so different in the other cropping systems. In the other cropping systems, the pesticide cost tended to be reduced, while the equipment cost tended to be higher, and mostly in cropping system number 5. Here you have a figure of the productivity of cropping systems, which we presented here over 12 years from 21 to 2012. You can see that productivity, so it's estimated in terms of gross product expressed as euro per hectare, accumulated over the 12 years. And you can see that the highest gross product was obtained with the reference standard cropping systems based on winter wheats here in green, winter barley in lighter green, and oilseed rape in yellow, with a quite regular and high growth product each year, whereas in all the cropping systems there were a trend to decrease the productivity, mostly because of the low productivity of some diversification crops, such as, for example, lupin, soybean, or spring barley in some occasions, that had lower productivity than the 3 main crops of the region: wheat, winter barley, and oilseed rape. So we found that in this experiment, integrated weed management tended to decrease productivity. Finally, we had a look to the profitability. With the indicator used was the net margin of the cropping system level expressed in euros per hectare, and we represented here the net margin as compared to the herbicide used over here. It's over 12 years from 21 to 2012, and you can see that all the integrated weed management-based systems tended to have a lower net margin as compared to the net margin of cropping system number 1, which was about 300 euros per hectare. But some systems were interesting. For example, system number 4, during the last part of the experiment, where sugar beets were replaced in this crop rotation by maize as a summer crop, you can see here that the net margin was about 260 euros per hectare, so about 40 euros lower than the reference standard system. So it's quite close to the standard systems, with quite a heavy decrease in herbicide use. But the conclusion here that in this experiment, integrated weed management tended to be less profitable than the standard reference. Thank you very much for your attention. If you want to know more about this experiment, you will find some articles in the literature describing some more detailed results. Thank you very much for your attention.